Okay. Last time we saw how we could find a coordinate transformation so that data would become, let's say, more manageable because we removed correlations between the coordinates. So we started with some matrix containing our data. So usually I need to remember the notation, but let's say if we call the elements x1 up to xn, x of 1, and here xn1 up to xnm. The columns contain our data items, and the rows were the specific coordinates of each data item. So that one single item of data was one column of this matrix. And so the idea was, after somehow normalizing this matrix by removing the mean value of each coordinate from mu1 to mu-n, the corresponding covariance matrix could be computed as, okay, it was a covariance between the different instances of the coordinates, so it was x times x transpose. This covariance could be written as could be decomposed so that we could find a coordinate transformation matrix V so that the covariance matrix would become diagonal. Okay, this was the main idea. Now, okay, this is fine. We also saw it working. However, this method, as I posted here, well, you can see it's asymmetric between rows and columns. Why? Because we are normalizing each row so that its mean would be 0. Its arithmetic mean would be 0. And this is what we actually want to do if we want to speak about covariance. But in many cases, we would like to treat this matrix as if rows and columns had the same importance. The idea, for example, is that if you have, if your matrix represents the TF-IDF coordinates of a set of documents, so that x11 and x1m the same matrix, if it represents the TF-IDF coordinates of documents, um, let's say, you can see columns as representations of documents, of course, but you can also see rows as representations of terms. Okay. In a sense, this column represents a vector of features of the first document. For example, what is the frequency of term 1, what is the frequency of term 2, down to what is the frequency of term n. The frequency normalized with respect to some criteria. For the same reason, this row represents a set of features of the first term. We are speaking of a matrix where we have n terms and m documents. Okay, so this term is characterized by what is its frequency in the first document, in the second document, and so on. And you see, in this case, we are interested both in analyzing our set of documents, which is important because at the end we want to, maybe we are building a search engine, so we are interested in what documents are similar and so on. But we can also be interested in similarity between terms. Well, maybe there are two terms that have similar features because they appear in the same document and so on, which is also useful when building a search engine because you want to identify synonyms. Okay, Google actually does that. Sometimes it also finds pages that contain different words because they are synonyms. Anyway, so even if the matrix is very far from being symmetric, okay, the matrix is rectangular, there may be many more documents than there are terms, or vice versa. But we want some sort of symmetry, so we don't want to treat a coordinate, one of the two dimensions, differently from the other. The other example, much similar to this, is the one where we have n items, m customers, and this is a ratings matrix. Again, a customer is identified by a column, which is a series of its features, which are in this case how he rated the different products. A product is a row, and of course its features are, well, for each user, how the item was rated by that user. Also in this case, we want to find, we may want to find similarities between customers, but we might also want to find similarities between items, products. So, today I'm going to extend somehow this method in order to get something that is, well, more general and that maintains equal treatment of the two coordinates. So, let's start from this matrix. Okay, matrix X. And let's keep the rest of the blackboard for other things. Okay. of all, I want to state the fundamental result that I'm going to apply. So, if X is what is n by m matrix, let's remain, of course, a real valued matrix. Of course, most results in this lesson and also in the previous one can be extended to complex valued matrix, which is the setting where most mathematicians put themselves in when they study these things. But of course, we are not concerned about imaginary or complex values here. Okay, we are only interested in numbers that we can understand. Then, if X is an n by n matrix, then we can write X as a product of matrices like this: U sigma dt such that, okay, I need, well, just for the sake of simplification, okay, maybe I should tell you what the rank of a matrix is. I suppose that you already know that, but the problem is that to define these matrices, I also need to know what is less, if the number of rows or the number of columns. So let me call R the rank of matrix X. What is the rank of a matrix? It's the largest number of independent columns or equally of independent rows that you can find within the matrix. I mean linearly independent. Or equivalently, the dimension of the subspace spanned by the columns of the matrix, or equivalently, the dimension of the subspace spanned by the rows of the matrix. The rank is always less than or equal to the number of rows and to the number of columns. You can define it in lots of ways. For example, it is the largest square submatrix that is non-singular, so that has a non-zero determinant, or that is invertible. Okay, so once we have identified the rank of the matrix, but anyway, we can assume that in the general case the rank of the matrix is the smallest between the number of rows and the number of columns. So, in order to get X from this, need so V to be an R by M matrix. Sigma is R by R, and U is, of course, N by R. Sorry, V transpose is R by N. Okay, we need to multiply an R by M matrix, an R by R matrix, and here an N by R matrix, so that U and sigma can be multiplied because they have the same number of columns here and row here. Sigma and V transpose can be multiplied, and the result is N by M. Then, let me see. I can, of course, let me speak about V rather than V transpose. Okay. So if V transpose must be R by M, of course V is M by R. The two matrices U and V are, let's say, column orthonormal, meaning that if you take two columns of V and you take the dot product of those columns, their dot product is 0, so they are orthogonal, unless, of course, they are the same column. In that case, the dot product is 1. And sigma is a diagonal matrix diagonal matrix, usually we can use this notation, diag, with the list of elements in the diagonal. Let's call them sigma 1, sigma 2, up to sigma r. It's an R by R matrix. And let's put them so that sigma 1 is greater than sigma 2, and so on. Sigma r. And all elements in the diagonal are greater or equal to 0. Okay, we can decompose this matrix in these three pieces. Pieces V and U are a sort of coordinate transformations that send X to a space where similarity is much easier to compute because it's given by a diagonal matrix. But let's see now how it works and how we can apply this. So, okay, I need of course to take this. This is our theorem for today, what we want to achieve. Next, I also need to explain you why I actually want to achieve this. The technique of decomposing one matrix in this way is called singular value decomposition. SVD. Okay. Let's see how we can find this decomposition first of all. Now, the actually, if this decomposition exists, so if we can actually write X as U sigma D transpose, then X transpose, what is X transpose? It's, well, remember, if X is this one, then X transpose is V sigma U transpose. Okay. Remember, when you have a product of matrices, if its transpose is the reversed product of all transpose matrices. Of course, sigma is diagonal, so we have no reason to transpose it. Its transpose is equal to the original one, so we get this. And X transpose is U sigma V transpose V sigma V transpose. But V transpose V is the identical matrix, the identity matrix, the matrix that has the diagonal matrix with ones on the diagonal, because we know that V transpose V is, because V is column orthonormal, it actually means this, okay? V transpose V is equal to, okay, here are the rows. So if you consider these as the columns of V, the columns become the rows of V transpose, then the generic element of the product is given by the product of one of these rows by one of these columns, which is always 0 unless the index of the row is equal to the index of the column, and then we have 1. So the product of V transpose V is the identity. So this becomes U sigma square U transpose. Same reason, X transpose X is V sigma U transpose U sigma V transpose. This is another identity matrix, so this becomes V sigma square V transpose. Well, at this point, you should notice that this first row here, X transpose, this product, is actually what we considered last time. So, apart from the row normalization, because we wanted every row to have a zero arithmetic mean, this is actually the covariance matrix that we considered last time. And this is actually what we got after applying the PCA method. Okay, the result of principal component analysis on X actually gave us a matrix U and a diagonal set of positive eigenvalues sigma, which in this case actually is called sigma squared. So, let me keep a small rectangle here where I write that U is the result of the principal component analysis applied to X. This is something that we are already able to do, meaning that we can find matrix U. And of course, here we have exactly the same situation with X transpose X. So B is the result of PCA applied to X transpose. The values sigma 1, sigma 2, sigma r that we need to complete this decomposition are simply the square roots of the eigenvalues that we find either with this decomposition or with this decomposition. We are guaranteed that they will be exactly the same. Okay, we have sigma squared both here and here. So, in order to find sigma, let's say sigma 1 up to sigma r are the square roots of the eigenvalues of the PCA method. Okay, so these are the rules by which we can find those matrices and numbers. Okay. Okay, actually there is a little more to this. I mean, you see, X is not a square matrix, it's rectangular. So actually there is a dimensionality issue here. For example, of course I run out of space as always. Okay, I assume that this is not useful anymore. And also this. Okay, let's see actually how we get this, suppose that our matrix X, which is a matrix of terms and documents, suppose that it has many more documents than terms. It means that our matrix is rectangular and it has many more columns than rows. Okay, so we are in a case where M is larger than N. Number of columns larger than number of rows. Then, of course, when we compute X transpose, if we look at the involved dimensions, we are multiplying a matrix with few rows and many columns by a matrix with many rows and few columns. What we get, of course, is a matrix with the same number of rows as the first matrix and the same number of columns as the second matrix. So we get, in this case, the numbers were, okay, n rows and m columns. These were n rows and m columns. M rows and n columns, so an n by n matrix. Okay. And once you compute the PCA of this matrix, so you take this matrix and you do the principal component analysis by the means that we have seen last time, we get that U sigma and of course U transpose are all n by n matrices. And here, of course, you get, I decided to call this sigma square this time. So here you have the values sigma 1 squared down to sigma n squared. Is that fine to here? Okay, now let's see what happens when you do the second PCA with the transposition. Well, in that case, if X has this form, then X transpose X is actually a very tall matrix with m rows and n columns by a very flat matrix with n rows and n columns, and the final result will be a much larger matrix than m by m matrix. Okay? This matrix is much larger than this. So at the same stage of the procedure, we get matrices that are even significantly different sizes. But now, okay, we make the PCA of this, let's call it covariance matrix. It's sort of covariance, but we didn't normalize the matrices, so it's not really covariance. And what we get is, this time, it will be the product of three large matrices, larger than these three matrices. And we call them V, sigma squared, and V transpose. Now the question is, how can this matrix and this matrix be the same as granted by the fact that both equalities lead to the same values? So how is it possible that this and this are the same? Actually, what you get is that this very large matrix has been obtained by matrices that have much less rows or columns than the equivalent square matrix. So the result has a rank which is much less than m. The rank of this matrix, of X transpose X, is at most n. So even this is an m by m matrix, its rank, the maximum number of independent columns or the maximum number of independent rows that you can find in here is much less, is at most n. So here you will find that the eigenvalues sigma 1 square up to sigma n square are the same here and here, and the remaining eigenvalues are zeros. Okay, so it's true that you can make the same procedure both with X transpose and with X transpose X. The fact that you get the same results is that it's because although one of the two matrices is much larger than the other, the information contained in the two matrices is exactly the same, meaning that you cannot have more linear independence on one side than on the other. The rank of this n by n matrix must be the same as the rank of this m by m matrix. So the largest of the two will for sure contain some zero eigenvalues. Now, what happens when you multiply, for example, this sigma squared matrix by this B transpose matrix? Actually, you see, when you multiply row by column this diagonal matrix and B transpose, you get that the first row of B transpose is multiplied by sigma 1. The second row of B transpose is multiplied by sigma 2. The nth row of B transpose is always multiplied by sigma n. The rows of B transpose that are below the nth row are always multiplied by 0. Okay, so these zeros here actually make the bottom part of B transpose here insignificant. It has no meaning. For the same reason, here we have this. So we can actually, we get exactly the same matrix if we keep sigma squared as an n by n matrix, removing the final columns and the final rows, and we remove the final columns of V, or equivalently the final rows of V transpose. So actually, we can write this product by okay, a let's call it I don't know, V dash. Okay, it's exactly V removing the final columns by the same sigma square matrix as there. So actually an n by n matrix, because the other values are 0, so they are influent, and here V dash transposed as an n by m matrix. Okay. Here, of course, I started by assuming that the number of columns is larger than the number of rows. Otherwise, the opposite would be true. This second PCA would find the smaller matrix. Here we would find the larger matrix, which we could cut exactly as in that case. So if m is smaller than n, then the two cases reverse. But at the end, okay, by taking this PCA decomposition and this PCA decomposition, we get that x is equal, so let's actually draw the matrix. This X matrix, which is n rows by m columns, is the product of U, which is n by n, sigma, which is also n by n, and V transpose, which is n by n. And by virtue of the PCA decomposition of last time, we know that U is a column orthonormal. Well, it's square, so it's both column and row orthonormal. And also V is column orthonormal. Okay. This is what happens provided that all of the n eigenvalues are different from 0. What can happen is also that the original matrix X has not a full rank. It can happen that the only thing that we know about rank is that the rank is always, is at most as large as the smallest between the number of rows and the number of columns. This is all that we can say about the rank of a matrix a priori. But actually, the rank of the matrix may be also smaller. If the rank is smaller, it means that, well, not all of the n rows of this matrix are linearly independent. There is some row that is linearly dependent on the others. So actually, this means that some of the smallest eigenvalues here might also be 0. It can happen that not all the n eigenvalues here are different from 0. For example, it happens in the example that we have seen last time in the laboratory if we eliminate the noise. If we set to 0 the noise variable, then all data points that we generate, if you remember the setting of the algorithm, lie on a plane, for example. This means that of all the data points, actually some are dependent on the others. There is a linear dependence on this. In this case, the smaller eigenvalues that you find in the PCA procedure are 0. We can check it tomorrow if you want. You know, if these are 0, it means that we can reduce the size of our matrices even more. So if here we have some 0 values, then actually the sigma square matrix can be reduced even more. It can be reduced to an R by R matrix. If there is linear independence, then R is equal to N. Then we are not reducing anything. In some lucky cases, we can reduce even more. And of course, removing these, if these eigenvalues are 0, then it means that we can remove the final rows and the final columns here, leaving U actually as an N by R matrix, and U transpose as an R by N matrix. And the same can be done here. If the last values here are 0, then this can be reduced even more, making this an R by R matrix, here an M by R matrix, and here a R by M matrix. Okay, so we will get even smaller matrices, R by R, R by R, and R by M. Oh, sorry, no. This, of course, remains N. Okay, if the rank of the matrix is less than the number of rows, then we can further diminish, restrict, make U smaller, and get this. Finally, you see this decomposition, when multiplied, gives the original matrix. So, even though these matrices can be smaller, they retain all the information that was in the original matrix. This is the important part. We're not, you see, in all these steps, we haven't actually removed any information. We only removed the zeros. Okay, so we made matrices as small as possible by removing the parts related to the 0 eigenvalues of the PCA decomposition. And what we get at the end is possibly smaller matrices. Okay, but what do we get from all this? Okay. I think I can raise. Okay. Of course, if the number of rows were larger than the number of columns, so that X is a tall matrix, always n by m, but n this time is smaller, then we would get at the end a product where U is a tall and thin matrix N by R. Sigma is an R by R matrix, and V transpose is an R by M matrix this way. Where both in this case and in this case R, okay, is the rank of the matrix, which is always smaller than, at most as large as the smallest of the two. Okay. Now, let's go to a practical problem that can be solved by this method. Suppose that our matrix X is a matrix of documents and terms, so that the column is a document. And suppose that we are building a search engine. The basic search engine is a program that receives a query, let's call it Q, and provides the documents that are most similar to the query. Okay, the documents that, for example, you see a query will be, of course, a vector in Rn. Okay, let's say a query, also a Google query, is simply another possible document, because it's a collection of terms. The terms that you write on the search bar. So a query can be treated exactly as any other document. It's just a vector of, it can be represented in the TF-IDF space. So Q, our query, is a vector in the TF-IDF space. Now, suppose that similarity between documents is measured by the dot product. Remember, we also called it the cosine similarity. So that, the similarity between one of the documents, D, and our query, Q, is simply the dot product between D and Q. We want to find the documents that bear the highest similarity to our query. So, we want to give back to the user the documents in our collection for which this dot product is higher. Okay, how can we compute the dot product of each of our documents by this query? Okay, we simply remember that our matrix X contains all documents, and that all documents are contained as columns. So we can get all dot products between our matrix of documents and our query by simply computing X transpose times Q. X transpose contains one document per row, so every time we compute one element of the result of this, we are multiplying one of the rows of X transpose by the Q column vector. So we get actually the dot product between that document and the query. So this yields exactly the vector containing the similarity between document 1 and query Q down to the similarity between document M and our query Q. By computing all of these, okay, after we have computed all similarities by this matrix product, we only need to get the top 5 values here, and the corresponding documents are the ones that are most similar to our query.
Shouldn't it be n, the number of rows? And
No, this is X transpose,
okay, so
because we have M documents. Of course, also the opposite could be done if we wanted to work on similarity between terms. So everything has a meaning also if we transpose everything. But this is the more intuitive. Okay, so at the end we take the 5 largest values and return the corresponding documents. Okay, what is the complexity of this operation? Of course, we are multiplying this X transpose is an M by N matrix multiplied by an N vector. So the complexity of computing this is the O of M times N. Now, now let's consider the singular value decomposition of X. Now, we can write X transpose as V sigma U transpose. And so actually we can write X transpose Q as V sigma U transpose Q. Now, so here we have V, which is an M by R matrix, times an R by R diagonal matrix, times U transpose, which is another R by R matrix. Of course, I'm considering the case, the first case there where M is larger than N. Sorry, R by N. Matrix. Times Q, which is an N by 1 matrix. Okay, how many multiplications do I need to do this? I have so you see, first of all, this operation gives exactly the same result, okay? Now in this case I have an R by a big O of R by N here. And let's see. This actually adds one multiplication for each element of this. So this is just a big O of R. So we can, it's negligible with respect to this. And finally, this N by R is multiplied by an R by 1 map. I mean, with this, sorry, I need to take more steps. So, okay, after this multiplication, which takes big O of R by N, what I get at the end is an r by 1 vector. Okay, it's r by n multiplied by n by 1. So I get an r by 1 vector. This is done in r multiplications. Simply, every element of this vector is multiplied by the corresponding eigenvalue here. And what I get is again an r by 1 vector. So this multiplication here takes an big O of m by r. So the complexity of this multiplication is the dominant term of these three big O's, which is either m by r or n by r, depending on whether m or n is larger. Okay? They are not nested. They are done one after the other. So here I have big O of r multiplied the maximum between m and n. Which is not significantly different from this, unless, you see, r, well, usually r is the smallest between m and n. So here I'm just multiplying the smallest between m and n with the largest between m and n. So I exactly get big O of m and n. Unless the matrix actually has a lower rank. If the matrix has a lower rank, then I get an advantage by doing this. Okay, so the first, if you want, negative result that we get is that these two are equivalent unless r is smaller than expected. Okay. But now we can actually get something much better by explicitly reducing the rank of our matrix. In fact, you see, let me draw. So let me redraw one of these products so that we can understand it better. So we have a matrix X, which is an n by n matrix, and we decompose it into a U matrix which is n by r. But in the general case, I can expect that r and m are more or less the same value. Okay, so let's assume the worst case. The worst case is when the rank is as large as possible. So in this case, r is equal to the smallest of the two, so it's m. Then we have a matrix sigma with values of sigma 1 down to sigma r. And finally, an R by M. So this is R to R. This is an R by M matrix, which we call the V transpose here. Okay, but here, do you remember that we put all the eigenvalues so that they were in order of magnitude. Sigma 1 larger or equal to sigma 2 and so on until the last sigma r and all positive. Okay, up to now the decomposition contains exactly the same information as the initial matrix. Because in fact if we multiply the matrices of the decomposition we get the original matrix. Okay, what happens if we intentionally remove some of the less important information from this? You see, this decomposition actually describes the importance of the information that you find in the various matrices. And the importance of the information is encoded in the magnitude of these sigma values. In fact, you see, you can see every element in X. You see, the generic element xij in X is actually the product of the ith row of U. Let's call it UI. If this is xij, you get it by considering the ith row of U. Let's call it UI. The j column of Vt, let's call it Vj. Why do I call it Vj? Because the jth column of Vt is actually the jth row of V. Times just a moment. Actually, I cannot write it like this. I need to keep here sigma and here put Vj. Okay. And if you expand this as in fact it's a row by column matrix, you get that this is the sum for having k go from 1 to r of u I k times sigma k times v j k. Is that okay? Or any problems? Okay, if you just explicit make the calculations explicit, you get that the generic xij entry of the matrix is actually this sum of products of the matrices here. But this gives us a measure of the importance of each of these VUIK and VJK elements of the matrix of the matrices U and V. Suppose that the last elements of this matrix sigma are very small. It means that from a certain value of k, okay, so suppose that here you go from 1 to let me write it. So the basic idea is that suppose that you decide that you only want to retain the first R prime values of this diagonal matrix, on the basis that the remaining ones are much smaller than the previous ones. Then what you are actually doing is, okay, you are removing some of these products from the original matrix. But the idea is that you are only removing those products that have a small sigma value. Okay. So you can replace xij by an x tilde ij by only taking the product of the first R prime, the sum of the first R prime contributions here, on the basis that you are only removing very small contributions from the final result. This actually amounts at replacing the values from sigma R prime plus 1 to sigma R with zeros. You take this matrix and you force the last elements to be 0. What you get, of course, now you are removing information, but what you get is an approximation of the original matrix. An approximation where you removed some of the less important information. The advantage that you get this way is that you are actually making these matrices even smaller. Because if you cut away the final values here by making zeros, you are actually removing the final the final rows from here and the final columns from here. Now, of course, if you make R prime much smaller than the original R, you get an advantage in these operations. Because here, it means that you are taking an arbitrary R prime, which can be much smaller than both M and N. Which is what can actually be done in practice. In practice, so things work like this. You start with the matrix X. You take the PCA, principal component, sorry, you take the SVD, singular value decomposition of X, from this singular value decomposition, you know that these values are in decreasing order. You decide to cut those values to a given number R prime, and then you cut all matrices according to the chosen value. So, you take an approximation UR by taking only UR prime, by taking only the first R prime columns of U. You build the approximation V R prime by only taking the first R prime columns of V. We get, of course, the approximation of sigma R prime, by only taking the first R prime values. And finally, you can build the approximation XR by UR sigma R V R transpose, which is an approximation of the original matrix X. Of course, you're never going to compute this matrix. You just need the pieces, because you can use the pieces to compute similarities like this. So, to give you a simple example, the idea is that if you have, as usual, a document matrix, a document term matrix, where, well, suppose that this is about programming languages, and this is the axis that counts the frequency of the term Java in the document, and this is the axis that something that always goes with Java is I don't know. Okay, let's say that people who talk about programming are often talking about Java. Okay, what we get from the PCA technique, was, okay, we found the best coordinates to represent this. What we get here actually is, okay, we decided to represent our documents on a different axis, where we have a more important contribution. We identify the most important contribution, the one corresponding to sigma 1, along here. And then we intentionally decide that the second contribution is not important and should be filtered out. So we intentionally remove the contribution along the perpendicular axis. This is what we do by equating to zero everything, in this case after the first value. So in a real document term setting, where we could have maybe m equal to, who knows, 1 million documents, and n equal to, let's be conservative, let's say 10,000 terms. Okay, we have always said that not all terms are equally important. Many of them can be discarded by means of different considerations, some are stop words and so on. But in this case, we can intentionally decide to go through the SBD decomposition and end up and decide to truncate everything to the first 50 dimensions, for example. Well, let's say 100, let's say 100. This means that even though the rank of our matrix is 10 to the 4, 10,000, so we in principle have 10,000 values here, we can decide to filter out everything after the first 100 values. So that we actually reduce the complexity of our search engine by a factor of 100. Means the complexity of multiplying this n by n matrix by a query, which was 10 to the 6 by 10 to the 4, 10 to the 10th, 10 billion multiplications, it could be reduced to 10 to the 6 documents times 100. No, sorry. No, it was R prime times the largest of the two. So, no, sorry. In this case, it was our query, of course, is large n. Okay. So it's actually 100 times 10 to the 4, meaning 10 to the 6, meaning 1 million multiplications. Okay. If we keep the data set as it is, we end up with 10 to the 10 multiplications. In order to compute X transpose Q for some query. Here, we reduce everything to a 10 to the 6, meaning 1 million multiplications. From 10 billion to 1 million. What do we lose with this? Of course, we lose a lot of information. We are intentionally keeping only the first 100 more important pieces of information, and we are removing the remaining 9,900 ones, on the basis that we are retaining the most information. Of course, we need to see how these values decrease. Well, the second point is that actually this calculation, well, I was a little cheating, because here we are never going to make 10 billion multiplications. Because the original matrix X has many zeros in it. It's a sparse matrix. And as you know, so we don't need to keep the whole matrix in memory. We only need to keep the non-zero entries. So this multiplication is actually, the number of multiplications here is actually much less. It depends on the number of non-zero entries in the X matrix. On the other hand, after we apply SVD, we lose the matrix sparseness. Sorry, the matrix becomes dense. And with the dense matrix, all multiplications must be performed. So these 1 million operations is the actual value. These 10 billion multiplications is probably a very large overestimate of the real number of operations that we need. But anyway, we probably get an improvement. We have a factor of 10,000 less. Okay. We actually get another advantage that I also referred to last time, which is by removing the parts with less information, we are probably removing a lot of unnecessary noise from the system. So that what we get at the end is possibly something that works better than the original system. Because we have identified the most important trends and removed everything that can constitute a distraction with respect to our actual goals. Anyway, these are numbers that are more or less confirmed in practice. I mean, it can happen then these numbers are more or less real, and this is a number that heuristically, by trial and error, you can actually end up when you want to build some search engine or something that evaluates your document set. Okay, this usually is something that you can expect if you want to retain the important information and remove what's not necessary from your system.
So that's actually a number of features you retain.
Exactly. This is finally the number of important features, while this 10 to the fourth is a lot more information, but many of those features are actually noise because, well, many are not necessary because they are just linear combinations of others. Although in this case it's not necessarily true. It's true if you consider term features within documents, for example. Here, for sure, you have that many features are linear combinations. Anyway, this is the number of important features. You're right. Of course, you can measure it somehow. Okay, maybe in one of the next lessons we will recall a few performance measures for this. Okay, I forgot to tell you why it's called the singular value decomposition. Turns out that actually these numbers are called singular values. And why are they called singular values? Well, actually this decomposition is very important in many areas of mathematics. And it's actually a generalization of the eigenvector and eigenvalue decomposition. In fact, if x is a square and, well, let's say symmetric, and also positive semi-definite, whichever is the meaning of these words, we actually get that x is can be written as a decomposition of u sigma u transpose, where sigma is the diagonal matrix composed of the eigenvalues of x, and u is the matrix whose columns are the eigenvectors of x. As we saw last time. Last time the covariance matrix was exactly in this condition, and we could actually decompose it like this. So this is what happens when x is a very good matrix with very good properties. And this is can be seen as a particular case of our singular value decomposition where u and v are the same matrix. In general, u and v will be different matrices, but we still can get some decomposition that is useful. If you look in general at eigenvalue decomposition of matrices, you see that eigenvalues actually work like the singular values that you see here. So they give somehow the importance of different directions in the space where this matrix operates. The largest eigenvalues mean large contributions, the smallest eigenvalues mean smaller contributions. So this generalization allows you to work with general matrices. Of course, it still works if you want to find similarities between terms instead of similarities between documents. Just transpose everything. And okay, so maybe tomorrow we can have a look at well, maybe a modification of the last program in order to show what happens when we do this kind of truncation. And maybe we shall also look at some exercises. Last words, one last word. This kind of transformation in the context of document term analysis is often called latent semantic indexing or latent semantic analysis. I'm not considering a very important difference between the two. The idea is that instead of looking directly at the words that compose a document, here you are actually looking at the concepts. So at linear combinations of words that represents different possible concepts, different possible semantics that can appear in your document. Usually concepts, important concepts in the document are less than the possible number of words. So this is why this reduction usually works.
So the number of features becomes the number of topics.
Becomes the number of topics, exactly. Of linearly independent topics. They're really important topics of the document. Of course, when you speak of topics of documents, you're usually thinking of some things between, in the sense of cuts, politics, and so on. In this case, you're not guaranteed that the topics will be actually understandable. The topics come out as linear combinations of words. And you're not guaranteed that you will understand why 0.5 cars plus minus 0.2 politics is a meaningful topic for your system. But actually, they are the trends, the directions that are actually identified as most important given the documents that you are considering. Okay.